In order to understand spectral classification, let's revisit a familiar spectrum, the absorption spectrum of the Sun. But this is the absorption spectrum of just one star, so how exactly do we classify the spectra of many different stars, especially when there are hundreds upon thousands of stars, each with a unique spectrum of its own? We can look at the spectra of these stars and align their main features to get a sense of how they can be classified. Granted, this sample here isn't a sample of spectra from hundreds of thousands of stars, but it is a good starting point. Those with similar features are grouped together, separate from those that have different features present in their spectra. If you recall, all these gaps in the spectra of these stars are absorption features, commonly referred to as the Fraunhofer lines of the spectra. Now, how would Fraunhofer lines affect the overall shape of this blackbody curve? Now, this should be a good review of Unit 4 in Module 2 from last week. To answer the question, we can look at the spectra of these stars. In this star spectrum, we can see that the main absorption features are these stark dips below the continuum of the curve, labeled by the various elements responsible for them. The same phenomenon can be seen here in the spectrum of this star as well, the only difference being the shape of the blackbody curve, with the lambda max of this one nearer to the shorter wavelengths, implying that this star is probably hotter than the first. This is exactly the kind of thing we think of when we say that stars can be classified according to specific features in their spectra. A great example of such features in a spectrum are the visible Balmer series lines. H alpha at 656 nanometers, H beta at 486, H gamma at 434, and H delta at 410 nanometers. Now, of course, there are more Balmer lines than the ones that we can see here, but these four are the ones that fall within the visible range, and these are the ones that we'll see in the absorption spectra of stars. Notice that the four gaps in the absorption spectrum perfectly match the four visible Balmer lines. Now, this is important because if we took the spectra of several different stars and lined them up in order of strongest to weakest Balmer lines, we would see them arranged in an order like this. This exact idea became one of the biggest astronomical projects in the early 1920s when the Henry Draper Catalog of Stellar Spectra was published between 1918 and 1924. With over 225,300 stellar spectra to sift through and classify, this task was assigned to the women working at Harvard College Observatory. Commonly referred to as the Harvard computers, these ladies spent countless hours going through spectrum after spectrum after spectrum of these hundreds of thousands of stars. Contributions from two women in particular were pivotal in developing the spectral classification system that we know and love today. One was Annie Jump Cannon, and the other was Williamina Fleming. Fleming was placed in charge of the classification of the Draper Catalog of Spectra after Henry Draper passed away, and his widow founded the Henry Draper Memorial to fund the continuation of the project. It was actually Fleming's idea to start classifying stars based on their levels of hydrogen abundance. Those with a lot of hydrogen had wider Balmer lines, and those with less had thinner. Those with the widest Balmer lines were classified as stars of Class A, and those with slightly thinner Balmer lines were classified as Class B stars, ranging all the way down to O or P for the spectra showing the thinnest Balmer lines. But then came Annie Jump Cannon. She simplified this classification system by removing some of the classes that were too similar to the others, keeping only those with noticeably different Balmer line strengths. Then she reorganized the remaining spectra based on the surface temperatures of the stars rather than the strength of the Balmer lines, resulting in the Harvard Spectral Classification that astronomers still use to this day. Class O stars are the hottest of these stars, and Class M stars are the coolest. An easy way to remember this classification scheme is to remember the phrase, "Oh, be a fine girl or guy and kiss me." The main classes of the Harvard Spectral Classification scheme are the letters O, B, A, F, G, K, M, which can be remembered through the mnemonic that we just saw, or other unique ones that you can make up or find online. Each spectral class is further divided into 10 increments, ranging from 0 to 9, according to temperature. This range is organized as hotter to cooler temperatures as you move from 0 to 9. For example, O0 is the hottest of the spectral classes, but even O9 is still slightly hotter than B0. So with that in mind, which star in each of these pairs of stars is hotter according to their spectral class? Would it be the A6 star or the K3 star? What about between G2 or F7? A4 or A1? B8 or M8? Hopefully you selected the correct answers in your head as the options became available to you. If not, give this video another watch or take a look at some of the recommended reading in this unit and see if that helps. In this table of the Harvard Spectral Classification, we can take a look at each individual spectral type and see a sample of a typical spectrum of a star of that type. Some key characteristics of each of these different spectra worth noting are their main absorption lines. Each spectrum, coming from stars of different spectral classes, has a different set of key absorption lines that pop out from it. In an O-type star, we'll see strong lines of ionized helium but barely any of the Balmer series. In a B-class star, the Balmer lines become somewhat more noticeable along with some strong absorption lines from neutral helium. Class A stars have the strongest Balmer lines, as we discussed previously. Now, these Balmer lines become weaker as we move through the lower temperature classes of stars, but instead we start to see spectral lines from ionized calcium, titanium oxide, and other singly ionized metals and molecules that begin to pop up. So if we revisit the set of spectra from earlier and rearrange it according to Annie Jumpcannon's method of classification, which was by temperature, we'll get this sequence of spectra. Their key features can be seen labeled here as having been caused by hydrogen, helium, carbon, oxygen, as well as potassium, calcium, and titanium oxide, all of which are elements that are common to stars. The strength of these features aligns with the expectations associated with the different spectral classes of these stars. Notice, for example, that the star Sirius of spectral type A1 has the strongest Balmer lines of all the spectra that we can see here. Altarf, the brightest star in the constellation Cancer, on the other hand, has a strong spectral line in the yellow region of the visible spectrum due to a large presence of sodium in the star's atmosphere. So we can kind of see how the characteristic spectral lines make for a good classification scheme that can be used in categorizing stars according to their temperatures. The Harvard Spectral Classification takes note of this and has proven to be such a useful tool in astronomy that it is very much still in use today. To sum up the various ways that we can classify stars, let's recap. We can use the peak wavelength or lambda max of a star's blackbody curve, which will also tell us the color of the star. Then, of course, color is associated with surface temperature. We also covered magnitudes in the previous video, including apparent and absolute magnitudes of stars, and we are just now wrapping up the spectral types. So, is there anything else? Well, as it turns out, yes, there is. We'll take a look at more of these methods in the next set of videos.